Hi guys, welcome to my channel. In this video we are going to solve a question about the reinforced concrete, and the question will be the analyze of a beam. The beam is doubly reinforced, you can see now on the screen. So let's solve the question. First we are going to make an assumption that the compression steel, so this steel is yielded. So the compression steel is going to be downward assumption, and we are going to then check it is correct or not. As we are going to assume that the compression steel has yielded. Okay, so we are going to write an equilibrium, and we are going to obtain the neutral axis from that equilibrium. And the equilibrium will be compression concrete plus compression steel equal to tension steel, because we just have these three forces. Okay, so compression concrete will be 0.85 multiplied with FCD. What is FCD? 16.66, the design strength of the concrete, and multiplied BW. What is BW? Is here 300 millimeter. Now you can see I write on the top of the cross section, and multiply with A. We don't know what is A. A is here. Okay, the depth of effective concrete, and plus CS. Sorry, what is CS? CS is the area of AS prime, the top steel. What is that? 942 multiplied FYD. Why FYD? Because FYD, we assume that the compression steel has yielded. So that means that we are going to use 365.22, okay? Equal to tension steel. What is tension steel? The area of steel multiplied with 365.22. And now from this equation, we are going to obtain A is equal to 49.68, and you know that A is equal to K1 multiply C, and K1 is equal to 0.85 because of the type of the concrete. Now if you look at here, it's here is C25, so it's K1 is equal to 0.85. And the neutral axis from this one, from this equation, we are going to obtain the neutral axis as 58.458. And now we obtain it, the neutral axis. So let's make a compatibility, and we are going to determine that the compression steel, we assume that it is yielded, but maybe it has not yielded. So we are going to check it. So let's make a check. Look at here, check is going to be like this. We're going to divide this length to this length. If you remember from the similarities of a triangular, this length over this length, sorry, this strain over this length, and we're going to divide this strain over this length. I guess you remember from the triangular. So let's write it. Epsilon S prime over, what is C? Look at here. This is D prime, this length. I'm going to show you. This is D prime. So I'm going to subtract D prime from the C. Let's write this right. So look at here. This whole is C, and this is D prime. When I divided strain prime over this length, so it's going to be C prime minus D. So C minus D prime. So what is C here? C is 58.458 minus 49.68 equal to 0.003, because we assume that concrete does also yielded. So it reached the yield point actually. Yeah, 58.458. And from this equation, epsilon S prime will be equal to 0.001460. Okay, so it is smaller than normally the yield point of this steel 0.001825. So we are going to write as the compression steel has not yielded. Okay, so the compression steel has not yielded. So what's wrong? So the assumption is wrong. Okay, the assumption is wrong. The neutral axis that we obtain is wrong. So we're going to find a new neutral axis. So let's write here new C value. Okay, sorry, new C value. We are going to obtain it. We have to find it, because if it is not yielded, let's write it if it has not yielded, we need to find a new C value. So let's write it. Actually, I'm going to write a formulation, but before the formulation, I'm going to write where the formulation comes from. So now we are going to make an equilibrium again. Okay, the equilibrium is the same actually. CC plus CS equal to TS. Okay, so let's write it. For the CC, 0.85 multiplied with FCD. What is FCD? Design strength of the concrete, 16.66 multiplied the BW, 300 multiplied A. I'm going to open A. A is K1 multiplied C. So K1 0.85 multiplied C. And plus AS prime. What is AS prime? Look at here. What is AS prime? 942 multiplied. We don't know what is the stress of this steel, because it has not yielded. So I'm going to write something like this. Look at here. From this compatibility, look at here. I'm gonna make an proof here. For example, for AS prime. Okay, for AS prime. What was AS prime? C minus D prime, right? Equal to 0.003 over C. Look at here. AS prime over C minus D prime, this length, equal to the strain of the concrete, okay? The yield point of the concrete over the C. Now look at here. We are going to write in the equations, and from that equations we are going to obtain the new C value. And also I'm going to give you a formula, okay? So it's going to be easier to determine the new C value. And from this, now we are going to obtain this value. Sorry, one second. Epsilon S prime equal to C minus D prime multiplied with 0.003, okay, over C. And now for this, we know that, okay, for this epsilon S prime, we know the formulation. But what is the formula of sigma? Stress in anything, okay? It is the yield point of that material multiplied with modulo of elasticity, right? So what is this one? This one we have it. This one is 200 gigapascal. So when I multiply with this, I'm going to obtain the new stress value that is going to be used in this the compression steel part. Okay, so this is going to be look at here. This is going to be this is going to be C minus D prime multiplied with 600. When I multiply with 200,000, okay, with this number, and I'm going to obtain 600 over C equal to tension steel. Okay, what is the tension steel force? Tension steel force, it is 1520 as the area of steel multiplied 365.22, and this is the design strength of the steel, because we just assume that this steel has not yielded. Okay, so from this now I have my equation. Look at here, I have now here as a C. When I multiply this as C here, I'm going to cancel this one, okay? And all parts, it's going to have a new C. And also this one will have a C. When I take this inside the, when I take this in, and here will be 0, and I will have now here as a equation with one unknown, and in the second degree you can see this is going to be C square, okay? It's going to be the second degree, so I can solve this equation. So when I solve this equation, I'm going to obtain the C as equal to 67.126. Okay. Now this is my new C value, but I'm gonna give you a formulation. Okay, a formulation here. Let's write it: CC multiplied C plus AS prime multiplied 600. And 1 second, I'm gonna check formula again. I don't want to make any mistakes. I'm really sorry. Yeah, minus tension steel multiplied C and minus AS prime multiplied 600 multiplied D prime equal to 0. When you apply this formula, we are going to obtain new C value. Okay, we are going to obtain new C value in the beam. So when I obtain this formula, this formulation, you are going to obtain the new C value. But now I showed you here how you can find the new C value from the equations, not just formula. When a teacher asks a question like that, you can use this formulation, but you have to solve this formulation from the discrimination. So delta discrimination, I guess you remember, B squared minus 4AC. Okay, do you remember this one? So you have to solve this equation. So this equation from the discrimination. But now you can use it as easier, but I recommend you to learn this one. You have to learn how the formulation comes from where. So if you don't know how to make this something into the formulation, you cannot understand the main part of the question. So now I obtained new C value. So let's make a compatibility and obtain the compression steel has yielded or not. So epsilon S prime over C, what is C? 67.126 minus D prime is 30, equal to 0.003 over 67.126. Sorry, yeah. And now from this equation, so from this formulation, I'm going to obtain the yield point of top steel equal to 0.001659. And now I told you here, if I want to find the stress will be the epsilon, okay? The strain multiplied with the modulus of elasticity, and we are going to obtain the stress inside that material, okay? So when I multiply this one, 0.001659 multiplied to 100,000, okay? And stress prime, actually this is the new design strength of the compression steel, okay? So 0.847 megapascal. And now we determine it, the new stress value also for the top steel. So let's make a compatibility also for the bottom steel. And for bottom steel, let's check how we're going to use it. For bottom steel, for example, I'm going to make one here. This length, okay, this epsilon s over this length, and I'm going to take the epsilon cu over this length. So let's write it here. The total length, the d normally will be equal to 480 minus c value 67.126 equal to 0.003 over c. And now from here I'm going to obtain the new strain value of the bottom steel will be equal to 0.01845, and this is greater than normal yield point of steel, ASY equal to 0.001825. So also this is tension controlled. Now you can see we solved the first part. Okay, we solved the first part. The first part is solved. So let's solve the second part. In the second part, it asks, estimate the balanced steel area, ASB, and it's over reinforced and under reinforced. So for two, for here, we are going to write as an equilibrium that our bottom steel and the concrete yielded at the same time. Okay, so 0.01825, let's make a compatibility over d. What is d? D the total length from here to until that point. D minus cb, this is cb. Okay, this is cb. D minus cb. Now I'm trying to find this length because I'm going to epsilon s over this length and epsilon cu over this length. Okay, 0.003 over cb. Actually, you know this one. This is 480. When I make this process, I'm going to obtain cb equal to 296.907, and A will be equal to 252.337.1. And now I obtain the CB and A. Do you understand how we are going to obtain CB and A? I guess now it is clear how I wrote here. Now I just make it here as compatibility, okay? Sorry. Now I just make a compatibility, so it's easy. So let's write an equilibrium and determine the balanced steel area, okay? So for the equilibrium, it is also be the same. Look at here, CS, CC, CC plus CS equal to tension steel. So 0.85 multiplied with FCD. What is FCD? 16.66 multiplied BW 300 and multiplied with A. What is A? 252.371. And this equal to, plus 942 multiplied the stress that we determined here, 331.847, because now it is the stress of this steel, okay? The yield point of the steel. 847 and equal to ASB multiplied 365.22, because we assume that here, look at here, we assume that the bottom steel has yielded. So from this we are going to obtain ASB 3791.543. Okay, now this is the balanced steel area. Okay, so let's make a compare the balanced steel area. What is AS? We are going to make a compare with AS and balanced steel area. Look at here, the AS is 1520. Okay, so the AS equal to 1520 millimeter square, smaller than ASB, equal to 3791.543 millimeters square. So now it is under reinforced. Okay, it has to be like that. If it is like this, it's under reinforced. It is a reverse, it is over reinforced. We don't want any cross section to be over reinforced. Okay, always we want it to be to be as the under reinforced. So let's solve the third part. For the third part, it asks us determine the ratio of steel in the cross section: row prime, row balance, row mean, and row max. We are going to determine the ratio of steels, and we are going to make a compare. So it is under reinforced and over reinforced again, because for the specifications of Turkey or any country, the reinforced it used in the cross section must be in a ratio, in a range. You cannot go over that range and make this design under that range also. So let's write it. Row, okay, row AS equal to over BW multiplied D. What is AS? So bottom steel, 1520 over 300 multiplied 480. This will be equal to 0.01055. So let's write here row prime. For row prime is equal to AS prime over BW multiplied with D. AS prime is 942 over BW, 300 multiplied 480, and this is also equal to 0.006541. Row balance, ASB over BW multiplied D. What is ASB? 3791.543 over BW, 300 multiplied 480, and this is also equal to 0.02633. So let's determine the row mean. When I determine the row mean is also equal to 0.8 multiplied FCTD over FYD. And this is also equal to this 0.8 multiplied 1.7. Sorry, yeah, 1.7 multiplied 365.22. And this is equal to 0.003956. Row max. Also, we have to determine the row max, the maximum, the ratio of steel. 0.85 multiplied with row balance. It's also will be equal to 0.02238. Now we obtain this all. You can see the all is determined. So now we are going to make a compare that our steel is under reinforced and over reinforced. Okay, again, so it has to be equal to row smaller or equal to row max. Let's make check. What is row? 0.01055 smaller than 0.02238. So it is under reinforced. Now also we make the compare. Now the third part also the salt. Let's find the fourth part. What is the fourth part? The fourth part is asked. Let's find the MR. What is MR? The moment can be carried by this cross section. Okay, the moment can be carried by this cross section. So let's find it. Let's find it. Let's go to the bottom page. Here, I'm gonna write it here also. Fourth part. For fourth part, MR is equal to CC multiplied D minus A over 2. This is the point of the compression concrete it acts. Okay, so plus CS multiplied D minus D prime. Now this is the moment can be carried by this cross section, the formulation. So let's write it. 0.85 multiplied FCD, design strength of the concrete, 16.66, multiplied BW, 300, and multiplied A. What is A? Let's check what is A. Actually, we determine it, but we are going to check it together because I don't want to write wrong. Yeah, this will be equal to, actually we didn't write it, sorry. Now I'm gonna check for you. And A will be equal to, right, let's write it here, 57.05. So let's write it. This will be BW multiplied with A, 57.05 multiplied 480 minus 57.05 over 2, okay, plus CS. What is CS? AS prime. What is AS prime? 942 multiplied the design strength of this steel. It is different because, you know, it's not 365 because it has not yielded. 331 and 0.847, and this is the design strength of the top steel. And multiplied D minus, what is D? D 480 minus 30 D prime. And from here, we are going to obtain MR as 142.59. Actually, we can write as 6. It's okay. 6 kilonewton meter. This is the moment can be carried by this cross section. You are going to obtain like that. Okay. Now the fourth part also, the salt. Let's find the fifth part. At the fifth, let's check the question and then we are going to write it here. For the fifth part, it says check it's okay or not for ultimate moment of the beam of given a 5 meter length. 5 meter length. Let's check. We have a forces here. Okay, we have forces, and there is simply supported normally, but I couldn't draw it here. Sorry, unless I'm going to draw it at this place. For example, this is our beam. This is 5 meter length, and we have a dead load as 15 kilonewton meter and live load as 10 kilonewton meter. And now let's find the design load. For the design load, we are going to, PD for design load will be 1.4 multiplied with dead load 15 kilonewton meter plus 1.6 multiplied with 10 kilonewton meter. Sorry, I don't need to write the kilonewton meter here because the unit shouldn't be right here. So this is going to be 37 kilonewton meter as the design load. And now from this, how I'm going to obtain? I'm going to obtain the moment as QL square over 8. Okay, what is Q? Q, the design load here, 37 multiplied 5 square over 8. And this will be equal to 115.625 kilonewton meter. And now this is the moment of this span. This span will be created by these forces. Okay, so let's check that our design can carry this moment or not. So we are going to make like this. For example, MR. What is MR? 142.6 greater than the moment can be carried. Sorry, the moment of this span, 115.625. So this is greater than this moment. So it is okay. We are going to write like that. The design is okay. That means that our design can carry this moment. This moment created by these forces. Okay. Now the question is solved. Thank you for watching. If you like these videos, if you want to see more of the videos, please subscribe and share with your friends. I'm going to try to do the better. If I did something wrong, please warn me. See you for the next question.